Dear students, welcome once again to this interesting series of visual classes. Today, we are here to study yet another topic from the lesson Electric Current and Resistance. The topic for today is Internal Resistance and EMF of Electric Cells. Let me first tell you what exactly do we mean by the internal resistance of an electric cell. दरअसल इंटरनल रेजिस्टेंस एक अजिहा कॉन्सेप्ट है ਜਿਹੜਾ ਕਿਸੇ ਇਲੈਕਟ੍ਰਿਕ ਸੈੱਲ ਵਿੱਚ ਹੁੰਦੇ ਕੰਪਲੈਕਸ ਕੈਮੀਕਲ ਰਿਐਕਸ਼ਨਸ ਦੇ ਇਲੈਕਟ੍ਰੀਕਲ ਕਨਸੀਕੁਐਂਸਸ ਨੂੰ ਸਮਝਣ ਵਿੱਚ ਸਹਾਇਤਾ ਕਰਦਾ ਹੈ। ਜਦੋਂ ਸੈੱਲ ਦੇ ਵਿੱਚੋਂ ਕਰੰਟ ਫਲੋ ਕਰਦਾ ਹੈ ਤਾਂ ਇਸ ਦਾ ਮੈਜ਼ਰਡ EMF ਜਾਂ ਵੋਲਟੇਜ ਆਊਟਪੁੱਟ ਇਸ ਚੋਂ ਕਰੰਟ ਨਾ ਡਿਲੀਵਰ ਹੋਣ ਦੀ ਕੰਡੀਸ਼ਨ ਨਾਲੋਂ ਲੋਅਰ ਵੈਲਿਊ ਵਾਲਾ ਹੁੰਦਾ ਹੈ। So, in this class today, we will discuss the definition of internal resistance and the factors on which it depends. We will also study the EMF of a cell. But wait, do you know the meaning of the EMF of a cell? Before I tell you the meaning of the EMF of a cell, let me share the learning objectives of the lesson with you.
After the completion of this lesson, the students will be able to describe internal resistance of an electric cell, explain the principle of the internal resistance, define the EMF of an electric cell, solve numerical problems based on internal resistance and EMF of an electric cell, differentiate between EMF and potential difference.
To have a systematic beginning of the topic, let us start with a proper definition of the internal resistance of a cell. Internal resistance of a cell is defined as the resistance offered by the electrolyte and electrodes of a cell when the electric current flows through it. It is denoted by small r. The SI unit for its measurement will of course remain as ohms. An interesting factor is that the value of internal resistance of freshly prepared cell is generally low and its value goes on increasing as the cell is put to more and more use. Overall, other factors on which the internal resistance of a cell depends are, first, the distance between the electrodes. Second, the nature of the electrolyte used in the cell. Third, the nature of the electrode. And finally, the area of the electrode immersed in the electrolyte. If area increases, internal resistance decreases. We are now to define another physical quantity, that is terminal potential difference of a cell, to understand things properly. Terminal potential difference of a cell is defined as the potential difference between the two electrodes of a cell in a closed circuit. That is, when current is drawn from the cell. It is generally denoted by V and is measured in volts. When the electric cell or the source of EMF is in a closed circuit, the current flows through the circuit. There is a fall of potential across the internal resistance of the cell. The terminal potential difference between the two electrodes of the cell is less than the EMF of the cell by an amount equal to potential drop across the internal resistance of the cell. Thus, the terminal potential difference of a cell is always less than the EMF of the cell in a closed circuit. It is important to be able to evaluate an exact value of the internal resistance of a cell mathematically. To do so, let us consider a cell of EMF capital E an internal resistance small r connected to an external resistor of resistance capital R and a one-way key K, as shown in these diagrams. A high resistance voltmeter V is connected across the two electrodes or terminals of the cell. If the key K is not closed, the circuit remains open. No current flows through the circuit. Now, the reading of the voltmeter is equal to EMF of the cell, as per definition of the EMF of a cell. When the key K is closed, the current flows through the circuit as shown here. Now, total resistance of the circuit is equal to capital R plus small r. Magnitude of the current I is equal to E upon small r plus r. Let this relation be called as equation 1, whereas the potential difference across internal resistance R is V equal to I into R. It is found that the reading of voltmeter capital V now is less than the EMF E. Here, capital V is the terminal potential difference of the cell. According to definition of terminal potential difference, V is equal to E minus IR. This is equation 2. Hence, if I is equal to 0, then V is equal to E minus 0 into R or equal to E. Generally, in labs, the internal resistance of a cell is calculated using a potentiometer. Let me show you how.
Formula used for this experiment is R equal to L1 minus L2 whole multiplied by R and divided by L2, where L1 and L2 are the balancing lengths without shunt and with shunt, respectively. A Daniell cell is used as the primary cell whose internal resistance is to be found. R is the shunt resistance in parallel with a given cell. First of all, tight connections according to the circuit diagram. The EMF of the battery and that of the primary cell are measured, and it is made sure that the EMF of the battery is greater than the EMF of the primary cell. The positive pole of the battery is connected to the zero end of the potentiometer and negative pole through a one-way key, an ammeter, and a low resistance rheostat to the other end of the potentiometer. The positive pole of the primary cell is connected to the zero end of the potentiometer and negative pole through a galvanometer to the jockey. A resistance box of small range is used as shunt resistance through a one-way key K2 in parallel with the primary cell. The plug-in one-way key K1 is inserted and the ammeter reading is noted. The jockey is pressed at zero end and the direction of the deflection in the galvanometer is noted. The jockey is pressed at other end. If the direction of the deflection in the galvanometer is opposite to the first case, then connections are correct. Without inserting the plug in the key K2, the rheostat is adjusted and kept fixed for constant EMF. The jockey is gently slided over the potentiometer wires till a point of no deflection is obtained on the galvanometer. The null point position is obtained accurately and the balancing length L1 for the EMF of the primary cell is noted. The shunt resistance is connected by inserting the plug into another one-way key K2. Adjustment is made from the resistance box connected in parallel with the cell. The jockey is gently slided over the potentiometer wires till a point where galvanometer shows no deflection is obtained. The null point position is accurately obtained and the balancing length L2 noted. Knowing L1 and L2, the value of internal resistance of the given primary cell can be measured.
Thus, the terminal potential difference of two electrodes of a cell is equal to the electromagnetic force of the cell when no current is drawn from the cell. The electromagnetic force of a cell is also written and spoken as EMF in short. Or in other words, the potential difference between two poles of the cell in an open circuit, that is, when no current is drawn from the cell, is called the electromagnetic force of the cell. Due to this EMF, a cell drives the charge around the circuit. Therefore, EMF of a cell is also defined as the energy supplied by the cell to drive a unit charge round the complete circuit. It is denoted by capital E. The SI unit of EMF is volt or joule per coulomb, denoted by capital V. The EMF of a cell is said to be 1 volt if 1 joule of work is performed by the cell to drive 1 coulomb of charge round the circuit. इत्थे नोटिस ए कीता जाना चाहिदा है कि किसे सेल वास्ते टर्म इलेक्ट्रोमैग्नेटिक फोर्स ਜਾਂ EMF ਗਲਤਫਹਿਮੀ ਪੈਦਾ ਕਰ ਸਕਦੀ ਹੈ। ਅਜਿਹਾ ਇਸ ਕਰਕੇ ਕਿਉਂਕਿ ਇਹ ਇਲੈਕਟ੍ਰਿਸਿਟੀ ਦੇ ਕੈਰੀਅਰਸ ਉੱਤੇ ਫੋਰਸ ਰਿਪਰੈਜ਼ੈਂਟ ਨਹੀਂ ਕਰਦੀ, ਬਲਕਿ ਕੈਰੀਅਰਸ ਨੂੰ ਡਰਾਈਵ ਕਰਨ ਲਈ ਵਰਕ ਡਨ ਪਰ ਯੂਨਿਟ ਚਾਰਜ ਰਿਪਰੈਜ਼ੈਂਟ ਕਰਦੀ ਹੈ। ਤੁਹਾਨੂੰ ਨਹੀਂ ਲੱਗਦਾ ਇਥੋਂ ਸੈਲ ਦੇ EMF ਨੂੰ ਇੱਕ ਹੋਰ ਤਰੀਕੇ ਨਾਲ ਡਿਫਾਈਨ ਕੀਤਾ ਜਾ ਸਕਦਾ ਹੈ। It can also be defined as the work done per unit charge to drive the carrier. So, it can very well be said that the EMF of a cell in volt is energy gained by 1 coulomb of charge as it passes through it. Thus, if I is equal to 0, then V is equal to E minus 0 into R or equal to E. So, the maximum possible value of V for I equal to 0 is E, which a cell can offer. As the point A is at the same potential as the positive electrode and the point B is at the same potential as the negative electrode, therefore, the terminal potential difference of a cell is equal to the potential difference across the external resistance R of the circuit. That is, between points A and B. So, according to Ohm's law, V is equal to I into R or I is equal to V by R. Putting value of I as equal to E upon R plus capital R, we have V equal to E upon small r plus capital R into capital R. Using the values of V as E minus IR from equation 2, we can write the internal resistance of a cell small r as E minus V upon I, which is equal to E minus V upon V into capital R. This is the desired relation for the internal resistance of a cell. Besides all the mathematical treatment that we did and learned, there are some important conceptual aspects about the internal resistance of a cell. These points are useful to us for they give us a better understanding of cells and their internal resistance. So, let us know them. The first thing to note is that the direction of current sent by a cell in an electric circuit is from positive terminal to negative terminal outside the cell and negative terminal to positive terminal inside the cell. It means that inside the cell, the positive charge flows from negative electrode to positive electrode. Then, the EMF of a cell is independent of the quantity of electrolyte present in the cell, size of the electrodes, and the distance between the electrodes. You may please also note that when current is drawn from the cell, then terminal potential difference of the cell is less than the EMF of the cell. Then, when a cell is charged by some other electric source, then first of all, the terminal potential difference of the cell is greater than the EMF of the cell. And secondly, the direction of current inside the cell is from positive plate to negative plate. It is also important to know the internal resistance of a cell cannot be measured using the resistance or ohms setting on a conventional multimeter, since it requires a current to be observed. However, it can be calculated from current and voltage data measured from a test circuit containing the battery and a load resistor. ਸੈੱਲ ਦੇ ਇੰਟਰਨਲ ਰੈਜ਼ਿਸਟੈਂਸ ਅਤੇ EMF ਬਾਰੇ ਦੱਸਣ ਤੋਂ ਬਾਅਦ ਮੈਂ ਤੁਹਾਡੇ ਲਈ ਕੁਝ ਦਿਮਾਗੀ ਕਸਰਤ ਦਾ ਇੰਤਜ਼ਾਮ ਕੀਤਾ ਹੈ। ਜ਼ਰਾ ਇਸ ਸਵਾਲ ਉੱਤੇ ਵਿਚਾਰ ਕਰੋ। ਅਜੇ ਤੱਕ ਸੈੱਲ ਦੇ ਇੰਟਰਨਲ ਰੈਜ਼ਿਸਟੈਂਸ ਅਤੇ EMF ਨੂੰ ਮੈਜ਼ਰ ਕਰਨ ਦਾ ਕੋਈ ਤਰੀਕਾ ਕਿਉਂ ਨਹੀਂ ਬਣ ਸਕਿਆ? ਤੁਸੀਂ ਜ਼ਰਾ ਦਿਮਾਗ ਤੇ ਜ਼ੋਰ ਪਾਓ ਤੇ ਮੈਂ ਇਸ ਕਨਸੈਪਟ ਨੂੰ ਅੱਗੇ ਲੈ ਕੇ ਚੱਲਦੀ ਹਾਂ। Well, there are still some points left to be told. First of all, it is important to note that during charging of a cell, the positive electrode of the cell is connected to positive terminal of battery charger and negative electrode of the cell is connected to the negative terminal of the battery charger. In this process, current flows from positive electrode to negative electrode through the cell. Therefore, V is equal to E plus I into R. Hence, the terminal potential difference becomes greater than the EMF of the cell. Secondly, the difference of EMF and terminal voltage is called the lost voltage as it is not indicated by a voltmeter. After having learned so much about EMF and the potential difference of cells, can you clearly differentiate between the two physical quantities? The EMF of a cell is the maximum potential difference between the two electrodes of a cell when the cell is in the open circuit, while the potential difference between the 2 points is the difference of potential between those 2 points in a closed circuit. EMF of a cell is independent of the resistance of the circuit and depends upon the nature of electrodes and the nature of electrolyte of the cell, while the potential difference depends upon the resistance between the 2 points of the circuit and current flowing through the circuit. The term EMF is used for the source of electric current, whereas the potential difference is measured between any 2 points of the electric circuit. Finally, EMF is a cause, whereas the potential difference is an effect. Let me highlight yet another significant factor. Why do cells or batteries fail? When a cell or a battery fails, It is typically because it has built up enough internal resistance that it can no longer supply a useful amount of power to an external load. If you measure the voltage of a failed cell or battery which is disconnected, you will usually find that it has a nearly normal voltage, so that a voltmeter is not a useful tool to judge the degree of life left in the cell or battery. If you connect the cell or battery to an external resistance, then you will find that its terminal voltage drops. This can be interpreted as dropping most of its voltage across its internal resistance so that it is not available for external service. The understanding of any concept or formula cannot be assured until we grill our brains with some questions. To ascertain that, may we solve some numerical problems related to internal resistance and EMF of cells. Consider this problem first. A battery of EMF 15 volt and internal resistance 6 ohm is connected to a resistor. If the current through the circuit is 0.3 ampere, what is the resistance of the resistor? What is the terminal voltage of the battery when the circuit is closed? Here, E is equal to 15 volts. The internal resistance of the cell is 6 ohms and the current through the circuit is 0.3 ampere. If capital R be the resistance of the resistor, then I is equal to E upon small r plus capital R, or capital R is equal to E by I minus small r. Substituting the values of E, I and small r, we have the resistance of the given resistor to be equal to 15 upon 0.3 minus 6. On calculating, this turns out to be 50 minus 6 equal to 44 ohms. Now, the terminal voltage of the battery is equal to the potential difference across capital R, equal to I into capital R. This turns out to be 0.3 into 44, that is 13.2 volts. Students, it will be worth solving another couple of numerical problems. Let's try this one. A battery of EMF 12 volt and internal resistance 4 ohm is connected to a resistor of 26 ohms. Calculate the current through the circuit and the terminal voltage of the battery when the circuit is closed. Here, E is equal to 12 volts. The internal resistance of the cell is 4 ohms. The resistance of the resistor is 26 ohms and the current through the circuit is to be calculated. Here, I is equal to E upon small r plus capital R. Substituting the values of E, capital R and internal resistance, small r, we have the current through the circuit equal to be 12 upon 4 plus 26 equal to 12 upon 30, that is 0.4 amperes. Now, the terminal voltage of the battery is equal to the potential difference across R equal to I into R. This turns out to be 0.4 into 26, that is 10.4 volts. There is yet another problem. A battery of EMF 24 volts is used to supply current through the combination of 3 resistors R1, R2 and R3 as shown here. When the key K is closed, the current through 5 ohm resistor is found to be equal to 3 amperes. Calculate the internal resistance small r of the cell and the currents I1, I2 through the resistors R1 and R2 respectively. Also, calculate amount of current if the key is opened. We will work out for the situation of the closed key first. Let Rp be the resistance of the parallel combination of R1 and R2. Then Rp is equal to R1 into R2 upon R1 plus R2, or Rp is equal to 6 into 3 upon 6 plus 3. On calculating, this comes out to be 2 ohms. If small r be the internal resistance of the battery, then the total resistance of the circuit R is equal to R3 plus Rp plus small r, or R is equal to 2 plus 5 plus small r equal to 7 plus small r. The current in the main circuit I is equal to E by capital R. Here E is equal to 24 volt and I is equal to 3 amperes. Therefore, 3 is equal to 24 upon 7 plus small r, or 7 plus small r is equal to 8, or R is equal to 1 ohm. Now, the potential difference across parallel combination of R1 and R2, V is equal to I into Rp equal to 3 into 2, which is equal to 6 volts. Therefore, I1 is equal to capital V by R1 equal to 6 by 6 equal to 1 ampere, and I2 is equal to capital V by R2 equal to 6 by 3 equal to 2 ampere. Now, for the case of opening the key, the total resistance of the circuit R dash is equal to capital R2 plus capital R3 plus small r, or capital R is equal to 3 plus 5 plus 1 equal to 9 ohms. Therefore, the current in the circuit I dash is equal to E upon R dash equal to 24 upon 9, which becomes 8 by 3 amperes. Dear students, it's time to conclude this lesson by looking back at the main aspects that we have learnt in this class. Internal resistance of a cell is defined as the resistance offered by the electrolyte and electrodes of a cell when the electric current flows through it. Factors on which the internal resistance of a cell depends are: first, the distance between the electrodes; second, the nature of the electrolyte used in the cell; third, the nature of electrodes; and finally, area of the electrodes immersed in the electrolyte. If area increases, internal resistance decreases. Terminal potential difference of a cell is defined as the potential difference between the two electrodes of a cell in a closed circuit, which is always less than the EMF of the cell in a closed circuit. The potential difference between two poles of the cell in an open circuit, that is, when no current is drawn from the cell, is called the electromagnetic force or the EMF of the cell. The SI unit of EMF is volt, denoted by capital V or joule per coulomb. It can also be defined as the work done per unit charge to drive the carriers. The EMF of a cell is independent of the quantity of electrolyte present in the cell, size of the electrodes, and the distance between the electrodes. The potential difference and the EMF of a cell are two absolutely different quantities. It's time to ask you some questions now, just to make you feel more confident regarding the contents of today's lesson. My first question is, what do you understand by lost voltage in a circuit? The answer is, the difference of EMF and terminal voltage is called the lost voltage, as it is not indicated by a voltmeter. The next question is, what is the direction of the current inside through an electric cell during its charging? The answer is, during charging, the current flows from positive electrode to negative electrode through the cell. I believe that all of you could understand the reasonings given in this lesson very well, and attending this class was a good learning experience for you all. Thanks for your attention and see you next time again. Goodbye.